Okay, so let me get started. It's a pleasure to have Maya Çakmak to be actually one of the first uh, speakers of our ROMER Center for Robotics and AI speakers. And Maya and I go, pretty long time. She was one of my first students, after which she, let me just read her bio. It's a pretty long one. She is now the Robert E. Denning Associate Professor of the Paul J. Allen School of Computer Science and Engineering at University of Washington, where she directs the Human-Centered Robotics Lab. She received her BS and MS degrees at the Middle Eastern Technical University, where she started her research career working at the Kovan Lab, which is the precursor for ROMER. She received her PhD in robotics from the Georgia Institute of Technology in 2012, after which she spent a year as a postdoctoral research fellow at Willow Garage, one of the most influential robotics companies. Her research interests are in human-robot interaction, end-user programming, and assistive robotics. Her work aims to develop robots that can be programmed and controlled by a diverse group of users with unique needs and preferences to do useful tasks. Maya's work has been published at major robotics and AI conferences and journals, demonstrated live in various venues, and has been featured in numerous media outlets. Tools that she and her students developed have been used by robotics companies like Sabioke, Fetch Robotics, and Hello Robot. She received an NSF Career Award in 2015, a Sloan Research Fellowship in 2018, and Early Career Spotlight Awards at RSS 2018 and Ishkai 2019. So, without further ado, I'd like to leave the stage to her, in which she will be presenting her talk on robot programming for all. And let me just tell you a small anecdote. When I announced this talk on Twitter, I received a message that there's there like somebody's niece who was a high school student, whether this robot programming for all would also include kids like that, thinking that this is like Lego programming or like all that. So I'm just warning Maya that among our visitors we may have a very diverse set of basically people from different backgrounds. And so, Maya, the stage is yours. Thanks.
Thank you so much. That's perfect, actually. It is robot programming for all, not just from, the tools itself, but also the research being as accessible as possible. So you already covered this, Eroloja, thank you very much. But I thought for that particular reason that we might have people who haven't crossed paths with me back at METU, or who might be inspired to think about studying some of these things. So I put this short bio there, sort of a timeline. And it was actually really fun to look back a little bit of these things. Ignore the sound. So when this was back in 2006, that's me in the video, and that's our robot Kurt. So this was my first research project. So after graduating from EE, I started a master's in computer engineering at METU and started working in Eroloja's lab, Kovan at the time. And this was our project. So we had this robot that would look around and try to understand what's in the environment and what actions it can do and what the result of those actions would be if it was executed. And then use that knowledge that it has learned from really experimenting with the environment like a child to make decisions on, for instance, how to navigate the environment. And that was really all of these things you just said, Eroloja, awards and the positions, etc. Really thanks to you, because that was the start of a wonderful research career for me. Very directly, when I started my PhD, my first project was actually taking that same idea of robots learning by trying things in the environment by experimenting. So having these fixed actions that it tries in the environment and looks at what is the effect, and using that learned information. So that I had this very low-cost robot from little dynamic cells, and a webcam as the head. Short robot, this is Junior, robot from my PhD. And basically what we did there was look at how people structure the environment for the robot when it's doing this type of learning. And this is very much like how parents would set up the environment around a baby for it to have experience. All right, so afterwards in my PhD, I started looking at, of course, that was a very simple thing to learn, but slowly moving towards learning things that are more complex in terms of what the robot can do. So things like manipulation. This is, again, a very social robot that I worked with called Simon, looking at learning two-handed manipulation skills, again, from a person and by talking to a person and asking questions. Here later on during my postdoc with the PR2 robot, much less social, more functional robot, looking at learning from demonstration from people, things like, folding a towel and manipulating objects. All right. And so the work that I'll talk about today is mostly from the later stage. So this is the beginning. Okay, so the long-term goal of my research is to build robots that can assist people with everyday tasks. So personally for myself, I'd like to have robots doing all the chores in my house by the time I retire. So basically I need to match sort of the decline in my capabilities and the increasing capabilities of robots. So we'll see if I ever get to retire from this job. But more generally, there are millions of people living with some form of motor limitation, whether it's due to an illness or an accident, and in many cases, simply old age, like I predict myself in the future. And these limitations, together with the way that the environment is built, basically for able-bodied people, leads to an inability to perform activities of daily living independently for many, many people. For example, here meet three of my collaborators. So these are, all three are quadriplegic. That means all four limbs are paralyzed due to different reasons. So Henry has had a stroke many years ago. Kavita has SMA, spinal muscular atrophy, so from birth, a condition that she has, and Tyler had an accident. So these folks need assistance with many types of activities that most of us take for granted. So things like being able to feed yourself or even scratch your face, right? We don't even think about it. So these people who collaborate closely with roboticists, Kavita herself is a roboticist, they know the potential that robots have in bridging this gap that they have in terms of physical limitations. And they don't want to wait for decades. Okay, I think I have still, many years of career to get there, but they don't want to wait. They want robots now. So how do we get there? And how do we get there quickly, as soon as possible? Now, the way that most robotics research aims to make assistive robots a reality, this is a dream for many, many years in robotics, is by developing robots that are fully autonomous with universal capabilities that can robustly function in human environments with all of its challenges, which are very highly unstructured. And this is like the holy grail of robotics. And this would be amazing the day we see this happening. But it's also extremely challenging, and we're making progress. There have been several revolutions. The Kinect came out, deep learning made a huge leap, etc. So we've made great progress, but we're still far from anything that we could confidently deploy in one of my collaborators' house, even though they're really lead users in robotics. And at this rate, we won't really get there even by my retirement. So it's unclear if we ever get there with this sort of approach. So instead, my research aims to get there much faster by basically challenging some of the different assumptions that we make in classical robotics approach. So first, instead of aiming for fully autonomous capabilities, I say that we go for semi-autonomous assistive robots, where the user is in the loop during the robot's execution of an assistive task. Second, instead of universal capabilities, I say that we embrace tailoring to the environment. So these capabilities will only work in a particular environment and will enable that user to actually do the tailoring. And we won't necessarily think about taking that robot out and having it function in every possible environment. And third, perhaps more controversially, I propose to co-design robot capabilities together with their environment and modify the environment accordingly to increase robot capabilities. So each of these is kind of a research agenda of its own, and I could talk for hours, but most of my work has focused on this second idea. So I'm going to focus mostly on that, but I'll take a moment at the end to revisit some of the other ideas as well. So we actually know that robots can do many useful things, tailored capabilities. And we know this from robot demos. So those of you who are roboticists have probably done demos. It takes, you might have seen lots of videos of robots doing things that you might consider useful. So putting dishes away, fetching a drink. There's one here where it's scooping the poop. Yes, so these won't work if you take them out of this environment. They only work in the demo environment. But what if the demo environment was my house, right? Could I just hire a team of engineers to make things work in this particular situation and have a demo forever that works, that does these things in my house? So I think of that as, it's an existence proof, it's possible. But even this very tailored solution that works robustly in one environment requires highly skilled programmers and very long development cycles, right? We prepare months in advance for these demos. It's not scalable. So we cannot have a team of specialized programmers working several weeks for every single home that we want to deploy a robot. So instead, we propose to enable the end users themselves. We have a different challenge now, to make it possible for someone who's not a programmer, roboticist, etc., to do the same thing that is currently done by experts and trying to do that efficiently. So that brings us to the title of my talk, Robot Programming for All. So robot programming is as old as robotics itself. Even the first robot had to be programmed. Surprisingly, not much has changed. And there's this awesome paper from Tomás Lozano Pérez. We call it the TLP paper in my lab, called Robot Programming. It was published the year I was born. It's very old. It's mainly focused on programming of industrial robots back in the day. But it's actually spot on about what makes robot programming unique and different from other types of programming that we learn in computer science, computer engineering. So things like an ability to reset a program for testing it over and over. We can't do this with robots, or how distributed and concurrent robot programs tend to be. It's great about enumerating all the requirements for robot programming. So we have some great foundations, but there's a new goal here, which is trying to expand that to be the notion of a robot programmer, right? So today, many robots are programmed with tools like ROS. This ROS stands up for Robot Operating System. And it's actually pretty amazing that you can just download this freely. I think back to Kovan days, or even my PhD, before my PhD, ROS didn't exist. And for, like you saw Simon the robot, I had to write my own collusion checker for that robot. That took me weeks and weeks. And right now you just download things and it's ready to go. But even now with, open source, with all the progress we've made, ROS programmers are still a very small population. So it takes several weeks to learn ROS. And that's if you're already a very good programmer of Python and C++. And we want to expand this to a much broader group. So you can imagine from, grandma and grandpa at home as programmers to, maybe a professional software developer at a robotics startup, or workers that a robotics company hires to do robot deployments and maybe get trained for a week or two. So there's a big spectrum there of robot programming. It's everything in between. So a lot of inspiration for these tools actually came from tools we developed for ourselves as, expert robot programmers. And so one unique experience that was particularly formative was in 2014. We actually got to deploy a PR2 robot in a private home in Arizona. And it's a very long story how we got this gig. I can tell you later. But we had many, many challenges, like how to even, talk to a millionaire who, could buy a PR2 robot and get their idea of what they wanted from this robot, to things like practical things, installing a ramp to the kitchen, because there was that one stair that the robot couldn't go, and a lot of the tasks were kitchen centered. And we were mainly hired to develop robot apps for this owner. So one of the first things we had to do was find out what apps he had imagined. So we interviewed him, etc. Of course, we had to shut down some of his crazy ideas, but we were able to settle on a set of 17 apps. We still have the list somewhere. That we could say, this is actually possible. PR2 can do this, and we can deliver software to do this within a reasonable time. Things like carrying packages from the door to the office, or fetching, he was a Red Bull drinker, so going to the kitchen, it was just stocked with Red Bull, and you had to pick out and bring your Red Bull. And these are end-to-end applications that require expertise in all parts of robotics, from perception, navigation, mobility, manipulation, etc. And building them would take, in our estimation, experienced ROS developers a month or two. So it was like creating a demo or multiple demos. But thinking about many apps simultaneously actually allowed us to see some patterns across the apps. And we realized that was some of the things were reusable. So we started building these tools for ourselves, or investing time in building these tools so that developing the apps would become simpler. Possibly eventually these tools were things we could imagine giving to the user themselves, so that he could continue to develop and edit some of his apps. So that was a big part of the inspiration. So in sort of trying to develop these applications that actually end users could use, we have some key questions to answer. So what is the right underlying programming language is the first one. And what is the right interface for that underlying programming language? So it's basically at two levels. There's what is underlying, the capabilities that we're going to create for the robot to be able to do tasks, and how do we interface that with the person? And there's different combinations. And of course, the answer is different depending on which level the robot is being programmed, what are the tasks being programmed, as well as the different types of users. And oftentimes there's a big trade-off between expressivity, how much we expose to the user, and they can, the number of different programs they can create, and intuitiveness. The more things we put, the more complex it gets. So we have to strike the right balance for different users. So to that end, a lot of my research in terms of process involves these things of first, a lot of interface design and inventing new ways to communicate with the robot, choosing the right representation and implementing robotic capabilities to allow that type of interface to exist, and putting our robots to test, and these tools to test with people to validate them and improve them over time. So what I'd like to do is basically go through and introduce some of the tools that we developed over the years. I won't have enough time to go into like all the technical details of these different things, but and not sort of, we've done lots of user studies and not describe them in a lot of detail, but just pick out some key insights and some observations, so you get a sense of what can be done with these things. And as I mentioned, this paper actually has a very nice way of separating the different levels of programming of a robot. So that's also what we use. So there's like at the sensor level, what can the robot see? What can the robot do in terms of actions? And how do we combine these things in high level tasks? How do we, what is the logic in how these things work together? So these are the kind of 3 levels of control. And we've noticed that each tool that we built usually falls within one level, and you need a suite of multiple tools in order to create some of those end-to-end applications. Okay, so let's start with something simple. So many of you probably have heard, or roboticists among you have heard of programming by demonstration, or another name is learning from demonstration. And one excellent interface for programming by demonstration is kinesthetic teaching. So this is where the person holds the robot from the arm and pulls it around to kind of show waypoints of the motion that it needs to do. And what happens is that the robot from that needs to replicate that same thing on its own. And there's more than 30 years of research on this specific problem with very impressive result. But the issue is that much of this work does not consider the end user. So the person who wrote the code and developed the algorithm for how the robot should learn from that data is the one providing that data. So they know exactly how it works. They have a flawless mental model, and they can give it the right type of data. Whereas when we take those tools and put naive users in front of it, they don't do the right thing. So a lot of my thesis work was, I assumed all I would have to do was to build the interface, but then I discovered that many of the assumptions made by these algorithms were violated by people even when they're sufficient, thoroughly instructed about what to do. Let's look at an example. So something like stacking cups. Most programming by demonstration techniques are data-driven, and they require multiple demonstrations of the task. So right there, already people will start questioning, I showed it already 2 times. Why do I need to show it a 3rd time? So people, one thing they bring is how they learn themselves or how they teach each other. And those expectations are reflected upon the robot. Second, even if they're willing to demonstrate many times, let's say you're paying them for demonstrations, they're not good at picking demonstrations that nicely cover the space and allow correct generalizations of that same task. And thirdly, which is very related to the second one, it's hard to know when you're done because the system is essentially a black box, and people are bad at testing the system. Those people who are bad at providing demonstrations are also bad at creating tests to make sure that it has learned what it's supposed to. And this actually includes myself. So the only way I got good at teaching robots when I was doing these experiments myself before I moved on to user studies was that I understood the underlying representation and I could inspect what the robot had learned by using some of those inspection tools or printing things on the terminal, things like that. So in this work, we wanted to give the same type of transparency that I had as an expert user through visualizations. So this required a simple representation that would be intuitive for people, that was visualizable while still being able to capture useful tasks. So we didn't want to simplify it such that, the robot cannot do anything anymore, but it's still, so again, striking that right balance. So here it is. Basically, an action is simply a sequence of end effector poses relative to landmarks in the environment that the robot can detect. So this was taken from previous work where multiple demonstrations of the robot would allow it to automatically assign poses of its end effector to landmarks in the environment based on regularities in the demonstrations. So instead, what we did was we assigned the poses to a landmark based on a very simple heuristic, which is proximity. So you can think of this as, each object has a bubble around it. If you're within that bubble, you get that pose that you're saving gets attached to that object. So then, here's an example. If that object moves around, that pose is going to move around together with the object as well. So as I said in previous work, this was automatically detected by multiple demonstrations and regularities in that demonstrations. Whereas here, there's a heuristic, and from a single demonstration already, we've made assignments, and it's something that's executable. Of course, simple heuristics make mistakes. Basically, what we want to do then is, instead of people having to provide many demonstrations to correct that mistake, we actually want to allow them to directly go and edit that mistake. So here's the example there. So here you can kind of see the visualization where, again, it's different poses that has been saved. Each of them has been assigned, so you can kind of see the link between the pose and the target object. And you can directly edit by changing those connections or even editing the poses themselves. So we take advantage of visualizations, not just in improving what is happening, a vision into the brain, but also directly being able to change the robot's brain surgery. Okay. And here, just to see different types of tasks that you can still represent with this very simple representation. So things like assembly of multiple objects with one another, changing the state of objects, multi-object organization, putting certain objects relative to another object, it nicely expands to multiple end effectors coordinated over time, disassembly, and even prehensile, non-prehensile kind of a combination task. That last one is my favorite. Yeah. Okay, so the task, and this is very expressive. We can, it's still at a low level action, but it's very expressive. And the task can get arbitrarily long. You can save as many landmarks as you like, as many poses as you like relative to as many landmarks. But expressing higher level task logic that you can see sort of quickly hits a wall there. So something like stacking 3 cups, which you're seeing in this video, it only works when it's 3 cups. So it's really, you have to make an action for stacking 1 cup, stacking 2 cups, stacking 3 cups. And of course, computer scientists, immediately you see that's not what you want. You want stacking n cups with a parameter, or you want to say stack all cups. And with kind of this just sequence of poses, we can't really express that. And indeed, in a lot of the most recent work in learning from demonstration, more and more people were looking at learning these high-level logic type things from demonstrations again. So, and you can see how that problem even gets worse, because for the robot to be able to infer correct program structures, it really needs the right set of demonstrations, and people again are not good at providing those. Similarly, that same idea of initialization by demonstration, so giving a demonstration to start a program, but then being able to go and edit that program. So we applied that same idea to a higher level programming. So this is a particular language we came up with called RoboFlow. It's a flow-based language. Basically, what we do is after there's a demonstration, we initiate that program, which is, of course, from a single demonstration. All you can do is a straight script of do this, do this, do this. And then everything, if anything goes differently than what was demonstrated, just fail safe. But of course, the person can go and say, add loops. A very simple edit there is to say, instead of being done at the end, go back and see if there's more objects. If you can detect the object, continue doing this. And if there's no object, then instead of failing, you're done, right? Very simple edit to make it a loop for that example of stacking as many cups as you like. So that's the example where, you can have multiple cups, it keeps working, dynamically more cups get added, it keeps working, etc. And that same idea, you can have things like in this other video, an action that works differently in different situations, right? If the object is close to the right hand and if you want it to be in the right hand, you go and pick it up. But if it's not, you push it towards the other hand as many times as needed until it's pickable by the other hand. So same idea with more higher level logic integrated by very simple edits by people. Okay, so we get the power just from loops and conditionals of expressing these more high level programming concept, but that's still not a general purpose programming language. And that can, for instance, have variables. So we quickly hit scalability issues because we couldn't really maintain state. And we realized that even children are programming their toy robots with such expressive general purpose real programming languages. And the secret was in many of these was that they use visual interfaces that basically remove the need to memorize the language syntax. And this is avoids basically making very simple mistakes and really scaffolds the programming process. So this was one thing we also wanted to try with some of these more real task-based robots rather than toy robots. So we took one of those interfaces, this one's called Blockly, and we started thinking about the real challenge here was, what are the blocks? What are we going to give people as the things that they can program with? And of course, we could provide simple things like, make the robot say things or display things on a screen. Those are actions we can say, will work robustly if you put a block there. But even something like pickup doesn't exist as a block. Robotics, there's still a lot of research happening, and we can't really give those as existing, robust blocks that are just going to succeed 90% of the time. So here the idea was to combine the low level and high level programming. So basically something that you program by demonstration, you could give it a name and it would show up in the high level program. And it's basically gave full customization again to the user by using this suite of tools. And with some integration of perceptual capabilities where the robot can, within that program, detect something and iterate, and maybe it's in an array and can look at the list of objects that it has detected, you can get to quite complex tasks. So this was inspired from Amazon Picking Challenge. This was around the time that was happening. So it's a crowded shelf with lots of objects that are not necessarily immediately graspable. So here the robot has, actions for getting a tool and using that to do certain non-prehensile type of manipulation once an object is graspable, going in and grasping it. Yeah, so this is basically an example of using that suite of tools to accomplish something that's rather complex. So the way that perception is integrated into this high-level programming is through simple, detect landmark block, and it's parameterized by known landmark types, like a crayon box or the shelf edge. But you can see that there might be many matches for something like the shelf edge there. So this kind of demonstrates the powerful use of general purpose programming language, where you can add logic and math. So you can look at, you detected all these different shelf edges. Which one is the one that I want to pull relative to? And again, not something that you can easily add with just looping or a kind of simple logic. Now let's talk a bit about the perceptual capabilities, right? A lot of programming focuses on actions and high-level logic. Perception is usually taken as, this is what the robot can see. Here, take it. So manipulation requires perception, of course, and many of our systems have some form of built-in perception, whether it's a generic landmark detector with a descriptor that comes with whatever is detected, or task-specific object detector, like with a very large, you can have a database of objects like crayon box, etc., and you detect that specific object in the environment. But unfortunately, you don't find something like shelf edge in any of these, right? There are no shelf edge detectors, and there's no shelf edge in, like, when you look at these big databases. So we kept basically running into limitations of perception over and over with the tasks that we wanted to do, and needed to build these custom perceptual detectors ourselves for these tasks. So that kind of inspired some of the next set of tools on the perception programming side of things. This example is what we call custom landmarks. Basically what's happening here, we have a point cloud of what the robot is seeing, and it's a very simple kind of tool that the person uses to crop part of that landmark to say, this is what I care about. And this is an example again of a drawer handle, something that's, you don't necessarily see in databases. Yeah, some examples here, things like the rim of the bowl. That's what my action is going to be relative to, not the whole bowl. So I only care about detecting where the rim is, things like that. And specifying landmarks with a single example, again, this requires new technical capabilities to localize these landmarks in new scenes. And again, I won't go into details here, but this was basically a modification of algorithm called ICP. And the key thing that made this work was to explicitly represent empty space as part of the landmark. So you get a good match, not only if the two objects, that's what typical ICP does, not just if the points themselves are well aligned, but also that the empty space around it matches as well. And it turns out this yielded something that we didn't think initially, that we could basically represent emptiness constraints as kind of a perceptual detection. So the examples here are, for instance, detecting if a box is empty. We could just have the empty box as a landmark, and then we could say detect empty box. And then if we find an empty box, we know that it's there, we can continue, etc. So other things like detecting an large enough empty space in the environment. Again, we would just needed an example of a large enough empty table, and it became a single block in the program. Or yeah, the other things, like you kind of randomly try to get something from the laundry, you look at your hand, you see if you've succeeded, or if something ended up kind of dangling from the edge. So, and then this ability of task-specific custom landmarks was basically key in programming many of these more complex tasks, like being able to grasp something just from seeing the rim of it, or larger objects, like you might not necessarily see the full thing, like the chair, but you just need to, as long as you can detect the edges, you can move it around. Okay. So this is one combination of tools that kind of we used to build this end-to-end capabilities. We've actually built a whole bunch of them, and there's a lot of overlap. So there's a lot of redundancy. These are not all very different tools. Some of them do the exact same thing, but have different types of interfaces. And, you know, this list is maybe like from 3-4 years ago. There's more now, and some of them we've already abandoned. Some of them you know, we've combined, things like that. So these is constantly evolving list, but each of them have sort of new insight about either how to communicate with them or how to represent things, so that earlier framing. So what I'll do is just give a few more simple examples from there. So one of these tools was looking at tangible programming, situated tangible programming. So being able to tell the robot reference objects that are in the environment. This is something that's hard. If you're sitting in front of the computer, the object is right there in front of the robot, and it's just very difficult to talk to the robot, tell the robot that's what I want, versus when you're there and you can just, you know, point to things. Of course, we do this naturally with our pointing and gestures and language, but here, again, to make it simpler for the robot, we developed these tags that are robustly perceivable by the robot and have a particular meaning for the robot. And what we found, I'll get to some of the interesting observations from this, but an extension of this is that the robot can also talk to you a situated way. So here it's using projections to say, you know, here's the program that you are building. It's over time, you know, compiling that program and showing you what it has compiled. And you can kind of detect errors that happen in your logic, or that the robot has seen what it's supposed to see. Another alternative for providing demonstrations here from another project in collaboration with more perception folks here, using robust detection of hands to look at interactions with objects, so something like bimanual manipulation tasks. And here there's, you know, the challenges is then to take that and turn that into a sequence of robot end effector poses, so transferring to the robot. And it's, again, a somewhat complex process to do this, but some of the interesting things that come out of it, that's somewhat different from the earlier tools. Things we couldn't do with the earlier tools is things like continuous motion. So things like wiggling things, you know, to try to open them. So teaching these more continuous movement-based strategies, or things like coordinating multiple arms and the timing of the thing. So pouring something while you're mixing. Another set of tools are inspired from taking a bit more inspiration from the constraints of the environment. So this is looking, you know, there's manipulation very generally, but looking at specific types of manipulation like cleaning, where there's lots of constraints, where you're holding a tool and the tool needs to be in contact with a surface that tends to be flat surface, oftentimes, you know, planar or vertical. So lots of structure in the task that we can make assumptions about and simplify what needs to be programmed. So this particular one looks at, you know, just showing the pattern of how to use the tool. And that's something that we can take then, it's like a puzzle piece, and you can stitch it around to make a full motion to cover different types of surfaces, including things like, you know, having obstacles, the surface being different sizes, different shapes, etc. Okay. Of course, it's fun to watch robots do cleaning, but this usually led to more mess in the lab than actual cleaning. So we have to go and clean the floor afterwards. Okay, so now let me go through some observations from some of these, having done many different studies with different tools and things that kind of come up over time in different studies. So themes that have emerged from studying these tools with people. So one of the common themes is that people prefer and are better at using tools that are not so intelligent, dumb tools that they understand very well, instead of something that might be actually impressive and useful at times, but fail in ways that they don't understand. So the example is in this study, where we had users provide a sequence of end effector poses to go through. It was better to have the robot go on a straight line between the poses than try to avoid obstacles, something that might seem intelligent, but because it was frequent enough that the robot would hallucinate an obstacle and try to kind of go around something that the person doesn't see and would shock the person. And when we did the simple thing, the non-intelligent of going on a straight line, everybody made the same mistake. The robot's hand would be below the table. They would move it around and save another pose. And the robot, of course, would try to go through the table. But people make that mistake only once. They immediately correct it and never make that mistake again. And secondly, they take responsibility for that error. They say, oh, I messed up. Whereas if the robot is doing something strange and they don't understand, it's like, what is the robot doing? Why did it decide to do this? So this is an interesting counterintuitive insight for me, that when we try to add intelligence to the robot, we need to ensure that people understand how it works and that it doesn't fail in ways that they cannot anticipate. Second important point, which I already raised, is that there's a spectrum of users. And this is not just across the different tools. Even with one specific tool, there might be different uses of that same tool. And this is the example here. For example, when I was at Willow Garage, somebody challenged me to do this Japanese t-shirt folding. And to this date, I'm the only one who has succeeded at this. Other people also tried, but it was basically just the intuition and the really nuances of how it fails, how it works, what you need to do to make it work. Whereas, in our study, this was kind of a much simpler task that people did. The same distinction also comes between novice and expert come in terms of efficiency. So we saw that people where even though they were equally successful at programming the tasks in the study, experts were much faster at doing the same thing. People with different backgrounds also react very differently to our system. So one of our study happened to have these 3 groups of people with different backgrounds, and people with programming language expertise would say, I hate visual programming. This is roboticists kind of said the same thing in a more kind way, that they would rather not use visual programming. Whereas non-programmers, who are arguably the exact target group for this type of tool, said they liked it for the exact reason that it brings, the advantage that it brings. They say, it's much better than Python because I can see if I missed anything. For tools that are targeted at different types of users, one of the key differences tends to be training time. For instance, training for this combination of tools in one of our studies where people, build the custom landmarks, program by demonstration, the different motions, and then combine those with the block-based programming. So very involved. It was multiple sessions. First they had 1.5 hour just training, and then they came back and actually did the tasks. Whereas for the situated tangible programming, we basically gave them this box of those little things, the tangibles, and we told them, try to make the robot pick something up. And with just even any instruction, just looking at those things there, of course, we iterated the design a little bit. They were able to do that pretty well, 75%, 90%. With zero training. They just start and do it. And with just 5 minutes of training, a lot of those errors also go away. So much different level of training needed. But again, even 1.5 hours of, to put that in a more absolute context, is quite impressive in my opinion. So if you think about some of these industrial robots that have similar capability levels, you have these pages and pages of user manuals. Oftentimes it requires you understanding, matrix transformations and algebra, kinematics, etc. Versus here, 1.5 hour, just, you come in and program the robot. Similarly, again, an example to put that in context, the crayon box example was something that, we were doing the Amazon Picking Challenge, and we had a summer intern kind of work on that for weeks, learning ROS, this and that, etc. Versus my student replicated that in 2.5 hours. Another example from a class project, 10 weeks of, team project, building this tic-tac-toe playing robot versus same thing in 3.5 hours. Okay. So one of my favorite results from all of this is the tools really let people to be very creative, and they use it in ways that we don't anticipate. So here are many examples of many different ways people program this towel folding task. And this is, we specify to them what is the starting state and the end state, but they use the robot in different ways, and even just kind of add things like, this specific one, let me see, like the correction at the end, the single-handed one, and then just fun stuff at the end. Again, from this other study, we thought, we had the answer set and we were going to just grade people's programs. And then turns out they came up with ways to program that same thing in a way that we hadn't anticipated from this study. Now, a lot of these observations are from studies in the lab, but some of our most important learning, and sometimes through failures, really comes from deployments of our tools. Some of our projects were actually motivated by the Savio case. So basically, after deploying their original functionality, this is a hotel delivery robot, and all it does is, go to the front desk, someone in the hotel orders something, and the robot, takes that object, takes the elevator and delivers that object. But, when the hotel started seeing this, they came up with ideas of other things the robot could do. And this would require Savio to, like their engineering team, to go and program that and compile it and send it to the user. And at some point they realized they cannot scale these custom requests. So we work with them to develop a tool for them to be able to quickly program those things after deployment. And they basically had a customer relations person, a non-programmer, who would go to hotels and program it on the spot. So it was very exciting to see all the different things they came up with. Savio themselves used this tool in trade shows where they would kind of do a custom thing depending on the team. They used it to test internally, etc. But also researchers used it for different use cases of the robot. And beyond hotels, they also had a customer, an airport that wanted these robots. And they said, okay, we don't care, it's an airport, it's a hotel robot, we'll make it work. And that particular airport example, this is CEO of Savio, he was a programmer back in the day, but non-technical person for a long time. He's himself kind of creating that demo at the airport. So another proud moment. And also these deployments brought out that even though this robot is created to do a very functional thing of take this bottle, like taking objects from point A to point B, the value that hotels saw was much more on the social side of things. People wanted to take selfies and wanted to interact with it. So a lot of the new cases that they wanted for our custom programming to create was related to social interaction. And that led to other types of challenges. So programming social robots, a whole different can of worms. Lastly, another way that we constantly put our tools to test is through outreach. So we do lots of demos with these tools. I basically have a demo every week down in the lab, and it never gets boring because it's different every time. So the visitors come and they have some idea of what they want to program, and there's always something interesting there. And this particular program is a summer camp that we've done with students with disabilities from around the state of Washington. And it has taught us a lot about accessibility of the tools. So some of these students are blind or deaf or are using an assistive device to control a cursor. So again, our tools got very improved in terms of these challenges or input challenges. And as well as sort of the ideas that come up with what the robots could do. So looping back here, so let me tie this back. So I motivated my work basically on end user programming as kind of a pragmatic alternative to developing universally capable and sort of universally adaptive robots. So the idea is to put the end users to work to be able to scale customization. We want robots to be customized and work only in one environment, but we can't really scale the way we're doing it right now. So we want end users to do that. But I think one of the most important, maybe more important impacts of this is the democratization of robot use cases. So enabling new applications that roboticists would have never imagined as like a task that they would take and start to work on. So for instance, like with, you know, all my privilege, I wanted robots to be cleaning my house, etc. when I retire. And if I hadn't met Henry, I wouldn't have thought of something like scratching my face or wiping my face as an app that would be useful to something. I wouldn't have picked that as a task to work on. And on the flip side, Henry couldn't have built some of those apps. So if you don't know Henry, he's been working with Charlie Cram from Georgia Tech for many, many years. So without those collaborators, he couldn't have really done these things. So it's really trying to bridge that gap. And with even the millions of people with physical limitations, they're all very unique and could benefit from the robots the most, arguably, among all people who could have robots. So the hope is that these tools will empower people to build such apps and to do useful things for them specifically. And I'm excited to say that this is not just a hope. During my sabbatical last year, I actually collaborated with Henry and this amazing team. We had a robot, this is a new robot, at Henry's house for a whole month. And we've been working with Henry since. So the robot is going back this summer. It's very exciting. So going back to some of these other ideas, that project with Henry actually started under the umbrella of making Henry control the robot directly to do tasks. So using it like a physical surrogate because he cannot move, rather than programming it. So it's kind of back to this idea of human in the loop operation rather than making it fully autonomous. And since I started as a faculty member, it was really a dream of mine to put robots in the home. But it was not practical until last year. We really wanted to do this. We have a fetch robot in the lab, and the logistics of it, you know, we had to rent a truck, and, you know, the house had to be changed in certain ways, etc. We still wanted to do it, but with the Stretch, this new robot that arrived, it became something that, you know, we can just put this in the back seat of a car and take it to a home, and it became much more feasible and exciting. It really opened up new possibilities. What we did was with Henry, we started with an interface that Stretch had already developed for themselves. And we did an exploration. This was in our laboratory kitchen here downstairs, where it aligned well with COVID. So this was a remote study. People would remotely control the robot to try to do these tasks. And we slowly started improving the interface based on the challenges that we observed. So that's what Henry started with. And it was first 2 weeks in June, Henry used this to do different types of tasks, like feeding himself, to operating a printer. I think I have a video in the next one. But the interface, he gave us suggestions. So he's very vocal about what works and what doesn't work. He's not shy to tell us that something doesn't work or needs to be improved. So these are some of the interfaces that over time we're both improving the robot itself, but also the interface. And really, this is a very slow customization of the interface itself. In terms of tasks, he got to do many different things, like operating the printer was for many years something that he hadn't done. I think the videos are causing issues again. No. And then very social things. So not necessarily just these very simple manipulations around the house, but something like playing cards with his family, or, he's very romantic. He wanted to give a rose to his wife. And that's something, again, we set up during the deployment. All right. And secondly, this other idea of co-design environment. This is something, again, during this deployment, we had an occupational therapist, turns out are brilliant people who go into homes and make them accessible for people with disabilities, make it possible for them with their limited capabilities to be able to do things that they want to do in everyday life. And this is what I think of robots as well. So robots, they have only wheel navigation, wheel accessibility, they have slippery fingers, they don't hear anything, they have limited vision, they have all these disabilities in human environments. And this is what the same thing that occupational therapists do for people with disabilities, we can also think about doing for robots. So I'll skip this part, but again, I've mentioned we've done this already when we had to put robots in the home. We've done it certainly in Henry's home. And again, some examples of our what our occupational therapists did, like all these handles, new handles on the objects in the environment so that it's robot accessible, or card holder that would make it possible to play a particular game. All right, with that, exactly at 10:30, I'm going to end and say thanks very, very much.